Casey Burke, June 18th. So, week 5 case connections, I'll be looking at 1 and 2. So, the first one is about a newborn girl. So, the first question that we have to cover is normal mechanisms of amino transfer in the body. So, amino acids in the body undergo specific reactions to help manage nitrogen waste. One key process is transamination, where an amino acid transfers its amino group to form glutamate. Glutamate then undergoes a reaction called deamination, which releases ammonia. This ammonia is used to make urea, a waste product excreted by the body to transport ammonia safely from where it is produced in the liver. The body uses the glucose-alanine cycle, and this cycle, pyruvate, is converted to alanine by attaching an amino group. Alanine travels through the blood to the liver, where it is then converted back to pyruvate, releasing the amino group as ammonia. In the liver, ammonia is often stored and transported as glutamine, a non-toxic form. The enzyme glutamine synthetase combines ammonia with glutamate to make glutamine. This process happens in almost all tissues. When the body needs to release ammonia from glutamine, another enzyme, glutaminase, breaks down glutamine into glutamate and ammonia. This typically occurs in the kidneys and intestines, and to a lesser extent in the liver. This breakdown process is especially active during acidosis, a condition where the body becomes too acidic. Studies have shown that the brain primarily gets rid of ammonia by converting it to glutamine in astrocytes, which is then exported out of the brain. To a lesser extent, ammonia is also managed by converting it to glutamate. The enzyme glutamate dehydrogenase, GDH, located in the mitochondria, plays a key role in this process. GDH can either break down glutamate into alpha-ketoglutarate and ammonia, or convert alpha-ketoglutarate and ammonia back into glutamate. So the next question that is asked is, how is the nitrogen transport connected to gluconeogenesis in the fasted state? So during fasting, the kidneys perform gluconeogenesis, a process that helps eliminate waste nitrogen resulting from amino acid breakdown. The carbon skeletons generated from this breakdown are also utilized as essential substrates for gluconeogenesis. So also, what urea cycle enzyme is most likely the deficit, and what urea cycle enzyme is least likely to be impaired? So, in many urea cycle disorders and some conditions related to arginine metabolism, there is an increased excretion of uric acid, which is an intermediate in the production of pyrimidines. Measuring uric acid levels can help identify different causes of high ammonia levels. Although hyperammonia is a feature of all urea cycle disorders, uric acid levels are elevated only in certain ones, such as ornithine transcarbamylase, OTC deficiencies, citrulonium, and arginosaucin aciduria. Elevated uric acid is also seen in disorders affecting the transport of dibasic amino acids, like glycerinic protein intolerance and HHH syndrome, and it is highly elevated in hereditary uric aciduria. So, next question is, which amino acid, if any, becomes essential as a result of this deficiency? So, OTC deficiency is a X-linked disorder affecting both males and females. It is considered the most common urea cycle disorder, with an increase of about 1 to 56,000. In OTC deficiency, carbamyl phosphate builds up and is converted to uric acid. The urea cycle plays a significant role in the synthesizing the non-essential amino acid arginine, which becomes essential in individuals affected by OTC deficiency. So the next one that we will be looking at is case study 2 of a 53-year-old male. So the first question is, under normal conditions, describe the metabolism and maturation of VLDL particles. So under normal conditions, VLDL particles, which are rich in triglycerides, are produced by the liver. These particles contain several types of apolipoproteins, including B100, C1, C2, C3, and E. With ApoB100 serving as the core structural protein, each VLDL particle has one ApoB100 molecule. The size of the VLDL particles vary based on the amount of triglycerides they carry. Increased triglycerides production in the liver results in larger VLDL particles. However, VLDL particles are generally smaller than chylomicrons. So the metabolism of these is in the peripheral tissues. VLDL particles are transported to peripheral tissues where their triglycerides are broken down by lipoprotein lipase LPL, releasing fatty acids. This process is similar to the metabolisms of chylomicrons, and high levels of chylomicrons and inhibit VLDL clearance due to competition. So the formation of VLDL remnants, as triglycerides are removed from VLDL remnants, also known as intermediate density lipoproteins, are formed. These IDL particles become enriched in cholesterol ester and acquire ApoE from HDL particles. So LDL particles are primarily composed of cholesterol ester and ApoB100, and they are the end product of the VLDL metabolism. In summation, VLDL particles are created by the liver, transformed into IDL through triglycerides removal, and eventually become LDL after further triglyceride hydrolysis and apolipoprotein transfer. So the next question is to describe how NAFLD could manifest and what potential processes could be impaired in order for this. So non-alcoholic fatty liver disease is what NAFLD stands for. It is characterized by the accumulation of triglycerides, TG, as fat droplets within liver cells. It is diagnosed when more than 10% of hepatocytes contain fat droplets, typically identified through a liver biopsy. So what are the key contributors to NAFLD? So increased fatty acids and triglyceride delivery. So having elevated levels of free fatty acids and triglycerides, and they're delivered to the liver, contributing to fat accumulation. Also, reduced fatty acid utilization. The liver ability to use fatty acids efficiently is diminished, leading to excess fat storage. Also, impaired triglyceride export. The liver's capability to export triglycerides to reduce, causing them to build up within hepatocytes. Also, a deficient beta oxidation. So the hepatocytes have impaired beta oxidation, the process by which FFAs are broken down, resulting in triglyceride accumulation. And lastly, excess carbohydrate intake. So excess dietary carbohydrates or increased glucose production in the liver stimulate de novo fatty acid synthesis, further contributing to fat accumulation. Interestingly, direct uptake of dietary fat plays a relatively minor role in liver fat buildup, though. So then the symptoms. NAFLD affects both males and females equally and is most common in individuals in their 40s and 50s, though it is also often can occur in children. Patients with NAFLD are often obese and may have hypertension. Common symptoms include fatigue and discomfort or pain in the right upper abdomen. Although many individuals may not exhibit any symptoms, physical examines often reveal mild to moderate liver enlargement. Patients with NAFLD may present with hyperlipidemia, which is elevated levels of the fat in the blood, hyperglycemia, which is high blood sugar levels, hyperinsulinemia, which is high insulin levels, and reduced insulin sensitivity, which is the body's reduced ability to respond to insulin efficiently. So, in summary, NAFLD manifests as fat accumulation in liver cells due to various impaired processes such as increased fatty acid delivery, reduced utilization and export of fats, impaired fatty acid breakdown, and excessive carbohydrate-induced fat synthesis. It commonly occurs in middle-aged, often obese individuals with symptoms like fatigue and abdominal discomfort, along with several biochemical abnormalities. Thank you for listening.